Yeah, we did it in like Science 9 and Math 10. I think you were part of both of those. Okay, before we get into factoring review, we are going to remember how to multiply. And we've done this a little bit in the last unit, so it should be nice and fresh. When you have two binomials like this, you have to multiply them together. And when you multiply them together, you use FOIL or you use your area diagram, whichever you prefer. I'm going to FOIL, or distribute. So my first terms multiplied together give me 6x squared. My outside terms multiplied together can be positive 30xy. My inside terms together give me negative negative xy. And my last terms multiplied together give me negative 5y squared. We then collect our like terms, right? We have like terms right here in the middle. We have xy and xy. So those can combine to become 6x squared plus 29xy. And then minus 5y squared. One of the reasons why we remember or remind ourselves to multiply is just so that we can see that two binomials multiplied together turn themselves into a trinomial. You also notice that there's some x squared terms in there, some y squared terms in there, some like terms in the middle. Factoring is all about going from trinomial to binomials. But to understand that, we just want to see, oh yeah, we're good at multiplying. That's why binomials become trinomials. We can also do it with even bigger things, such as these two trinomials multiplied by each other. In this case, almost everyone in the room uses the area diagram. Some people still use distribution. If you want to do that, that's fine. So we're going to multiply this using our area diagram. So that's where you set up nice little grid. And you go 3x squared plus 10x minus 9. Then down the side, you do the other trinomial, which is x squared, and then 2x, and then 1. And you create this little grid, and you fill out the grid, right? So the column and the row multiply together to create whatever's in the middle. So 3x squared times x squared will become 3x to the 4. You can add your exponents together. X squared times 10x is 10x cubed. X squared times negative 9 would be negative 9x squared. Three x squared times 2x, 6x cubed. Okay, coefficients go together, add your exponents. 2x times 10x would be 20x squared. 2x times negative 9, negative 18x. And these things are all going to be the same because you're just times it all by 1. So 3x squared plus 10x and then minus. Yep.
So is that all one?
Yeah, so all these numbers that I have in red, like all these things, these are all individual terms that are all going to be combined to be an answer. So we need to write all these out in one big row. Now that's a long thing to write out in a row. So what I do is I try to look for like terms within the grid and then just combine them as I go. So for instance, this first thing in the grid, 3x to the power 4. Do I have any other x to the power 4s? No. So then that is going to be one thing that comes out. And if you want, it sometimes helps people to like just cross it out so I don't recount it. And if I do this properly, then everything should have a cross through it when I'm done. My next term was 10x cubed. Do I have any other x cubes in here?
6x cubed.
So I have 10x cubed, 6x cubed, that's plus 16x cubed. And you see that'll save you from writing out a lot. If you're just doing your combinations as you go. Do I have any x squared terms? Yeah, I got 3 of them. I have negative 9x squared plus 20x squared plus 3x squared. So in your calculator, you're going to go 3 plus 20 minus 9, right? Figure out that you have yourself 11, 14. plus 14x squared. And again, you're going to cross all those off. Cross off all my x squares because I've used them all. My x terms, negative 18x plus 10x is going to be negative 8x. And my last one is negative. And if you did that properly, you should have everything crossed off. Everyone remember that? And they're like, yeah, okay, that's good. Hopefully that's good. All right. Factor. So now we're going to factor things. Factoring is like unmultiplying. You should hopefully remember this from math, or math 10. And there's a whole bunch of different ways you can factor. The very first type of factor we look for is called a common factor. The blue on blue looks really good. Right? So you always want to check to see right off the bat, are there any common factors? And we call it a greatest common factor, a GCF. Hopefully that term, you're like, yeah, I kind of remember what that is. A GCF is something that could be divided out of every single term. So if you look at this thing right here, and you look at the coefficients first, so the numbers. Is there a number that could divide into all three of those numbers? Gotcha.
5.
Yeah, 5 could divide into all of those. So 5 is going to be part of my GCF. Because that's the biggest number that could divide into all three of them. Yeah.
I don't remember what.
It's coming next. Yeah, I'm working there. Yeah, you're right. So Cameron makes a good point. She says you could also now look at the letters, and you want to check to see, can I take letter out of all three of those terms? Do they all share a letter?
Yeah.
What letter? W. Now, how many W's am I going to take out of this thing? You're going to take 2 out. And the way you know is look at the exponents. So you want to take whatever the lowest exponent is. In this case, the lowest exponent was W squared. Yeah, Caleb.
So it's not subdivision, it's not dividing.
I'm dividing this out of all three of those individually. So you're going to see in a second. And I'm just about there. This thing that we just created, that's called our GCF. Now what we do with our GCF is we divide every one of these terms by our GCF. Which means I'm going to have a GCF, and then I'm going to be left with a bracket, and I'm going to be left with whatever's on the inside after I divide. So the very first term was 15W to the power of 4. I want to divide that by 5W squared, which was my GCF. What's 15 divided by 5?
3.
3. What's W to the 4 divided by W squared? Get this. Yep, W squared.
Isn't there a law regarding dividing?
Yep. You do subtraction. So it's the top exponent minus the bottom exponent.
That one just seems
Yeah. All right, we're going to do this again. So now you have 5W squared divided by 5W squared. This is one that people usually mess up because they go, well, it all cancels. But it doesn't cancel. There's something there. What's 5 divided by 5? Probably. Yeah, 1. So I need to show plus 1. Like there's something there. It's not just all canceled out and gone. Now our last one. We'll do it again. Divided by 5W squared. Negative 25 divided by 5 would give me negative 5. W cubed divided by W squared would give me
W1.
W. Yeah. And you can put W to the power of 1. I'm just going to leave it W if you don't usually write that power 1. What we just did, that's called taking out a greatest common factor. Any questions about that? Yeah. Yeah, so if you want to check your answer, you would just look at your question and you would multiply that back into all three terms. and that would show you that you did it right. So you should do the exact same thing as the original question. Yeah. Yes. At this point, yeah. That's as much as we've done so far. Yeah.
If you have the GCF, but it's not as much difficult, can you further simplify that?
Yeah, that's a good question. So you always want to make sure if it is a GCF, okay. I was like, what are you looking at? You look in the brackets, and you could check again for a GCF. So is there a number that can divide into 3, 1, and 5? No. Do all of these have a letter? No. So then you definitely are done. But that's how you would check. Yeah, that's good too. Yeah. Yeah, you would add any like terms. Yeah, if you could. Okay. I want you to try to remove a greatest common factor from both of these questions. Okay? So you just think what we just did. And I'll write up my answer on the board. You look at the numbers first and try to find the biggest number that divides in all three.
So how do you just guess?
You can just guess and check, yeah. So use good numbers.
They taught us a method before.
We did those tree things. That's a lot of work. You don't have time to do that.
Factor trees.
Yeah.
Factor trees. Very hard.
The first one people seem to do pretty good with, right? People got that the GCF was 6x squared. You all did your division. It looked pretty good. A common mistake that was popping up was when you divide this middle term by 6x squared, 24 divided by 6 is 4, but the x squared divided by x squared is just equal to 1. They cancel each other out. So there's no x there left in the middle term. All right, down here. The issue that I ran into. So I said I wrote up an answer on the board. It wasn't the fully simplified, correct, factored answer. The reason it's not, I underlined it. Does anyone see what they notice when I underline those numbers? Yeah, Blake. Yep, by what number? 2. So all of these numbers can be divided by 2. So what I need to do is take another GCF out of these 3 things inside the brackets. And when I take that 2 out, it comes out front. And when you have 2 coefficients out front, you multiply them together. So you're going to end up with 12xy out front. And then on the inside, you're going to get xy cubed, 3xy cubed. Plus 5x squared minus 7y squared. Now, if you look, you notice that 12 was the actual GCF of the original question, but I only saw that 6 divided into all those things, which is why I got myself with the problem I got myself.
So you pretty much just create one for yourself.
Yeah, basically. By not realizing that the biggest number was actually 12, I just created an extra step for myself. You know. 2-0? Good question. So if you look at these 3 things, you notice that there are y's and there are x's, but there's not a y in all three of them. This middle one's missing a y. And there's not an x in all three of them because the last one's missing an x. So you need to have all three of them. Awesome. Difference of squares. So the second type of factoring that we are going to learn, we've done GCF, which is the first step of every question. Whenever you need to factor, the very first thing you do is GCF. The second type of factor we're going to look at is when you end up with a binomial. So difference of squares is only for binomials. So make sure that's like nice and clear to you. Right here is step by step how you do it. So if you ever need to look back and read, you feel free. What I'm going to do is show you a question, talk about it, and actually do it. So here's a question. It says factor it. You look at the question. You notice that it's a binomial. If it's a binomial, that means I need to check to see if I have a difference of squares. We're going to talk about that term for a second. The word difference in math means what? Means subtraction. So the word difference means subtraction. So if I'm looking for a difference of squares, I have to have a subtraction sign somewhere in this question. In this case, I have one right there. So that's the first thing you got. The next thing you need to know is the word squares. So they're talking about is perfect square numbers or perfect square terms. What's an example of a perfect square number? 9 is a perfect square number. What's another perfect square number? 4 is. 16 is. Give me one more. 25 is. Anyone know where I'm getting these numbers? It's from your perfect square chart, right? So 2 squared is 4. 3 squared is 9. 4 squared is 16. And you can go on. If it's a number that you could square root, it's a square number. You can. So I need to look at this thing and ask myself, do I have perfect square numbers? I do. 4 is a perfect square number. 9 is a perfect square number. The next thing I need to ask myself is, do I have perfect square variables? All that means is that you have an even variable. Okay? So you have a number of a variable with an even exponent. Do I have that? Yes, I do. That thing has an even exponent. I could square root x squared and get something whole. Yeah. This thing is a difference of squares. It's a subtraction of all perfect square terms. That means we can factor it. In order to factor it, what you do is you square root each term. So what we're going to do, we're going to square root this term, square root that term. The square root of 4 is 2. The square root of x squared is minus. The square root of 9 is 3. Put that thing in brackets. So that's your first binomial. And you'll notice that when we factor, we usually end up with 2 binomials. That's usually our goal in the end. It wouldn't make sense if this thing just became this thing, right? But these are definitely not. So what you need to do is you get one set of brackets, and now you need a second set of brackets. And that second set of brackets is the exact same as the first, but the symbol changes. So it's 2x, and now it's a plus 3.
Is it a negative 2x?
Nope, the 2x stays the same. Good question. That is completely factored difference of squares. And if you're not sure, you could multiply them together and you should get the same thing back. So why does the 2x stay the same? Good question. What you'll notice is, remember the term conjugate? Remember how we talked about that before? And remember how we said when you multiply by conjugates, meaning the exact same thing but with one opposite symbol, that it always canceled out those middle terms and left you with the first things and last things together? That's exactly what we've done here. This is just going backwards and creating that conjugate situation. So you need these terms to be the same so that you create that 4x squared. It's just that middle symbol that changes. And that's what deletes out those middle terms that we did last week.
What is this one?
Yep. Okay, number 2. We have a binomial. Whenever we have a binomial, we need to look for a difference of squares. Now, what's the very first thing I said you want to check for? A GCF, right? I said that's always, always, always the first thing you check for when you're factoring. So is there a GCF here? Is there a number that could divide into 16 and 64? Yeah, what would be that number? 16 divided into both? It definitely does. So if you divide both of those by 16, you now have 16 bracket x to the power of 4 minus 4y squared. So that's like a brand new question for us now. If you didn't GCF, you can see how much more difficult this thing would have been. So you always, 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 first step, do I have a GCF? Now you check and you say, do I have a difference of squares? Well, do we have a subtraction symbol? Definitely. So that's the first thing we needed. The second thing was, do we have perfect square numbers? And in this case, we do, because number 4 is a perfect square number. Do you have perfect square variables, meaning that you have even exponents on each variable? You definitely do. X to the 4, y to the squared. That means we have a difference of squares. So we can factor it by using the difference of squares method. What do we have to do with the difference of squares? Square root of. Do I have to square root this 16 out front? No, that's a coefficient. That thing just stays out front the whole time. So that 16 is still out front. Now we're square rooting each thing. So x to the 4 square rooted would be x squared. You just divide the exponent by 2. Minus 2 and then y. The square root of y squared is just y. I need 2 sets of brackets, right? What's the second set of brackets going to be?
Same thing, different symbols.
Same thing, different symbols separated. Perfect. That would be your answer. No, that's a good question. So what I have seen a lot of people do is they'll go 16x squared minus 2y and then 16x squared plus 2y. Remember with multiplication, order doesn't really matter on things. So it's not like it's 16 times 2 binomials here. It's just 16, and then this binomial turns into 2 binomials. We don't need to add another 16. No, it just stayed there. It's just a coefficient over.
Why doesn't this stuff come out when you like square root it? Square root.
Oh, why is nothing coming out the front?
Yeah.
That's only with GCS that happens. We're square rooting to become this. We're not dividing anything out. Things only come out front when you're dividing them out of it. You may. Alright.
No.
These two, a little bit trickier. I'm going to do number 3 with you. I'm going to let you try number 4 on your own. Why does this one look so much more difficult? Fractions, right? And fractions just make things look more difficult. But with difference of squares, it's really not any more difficult. All we're going to do is we're going to look at this thing and we're going to ask ourselves the same questions we asked ourselves the last 2 times. Is there GCF? No. No numbers dividing into 64 and 1 over 8. Is it a subtraction question? Yes. All right, good thing. Do we have perfect square numbers? That's where this can be a bit of a confusing question. So 64 is clearly a perfect square number. But is 1 over 9 a perfect square number is where things get difficult. And I see people are going, yeah, it is. And the way you can tell is look at the top and look at the bottom. And if both of those are perfect square numbers, then that's a perfect square number as well. So for instance, number 1 is a perfect square number that most people forget about. What's 1 squared equal to? 1. So 1 is a perfect square number. Is 9 a perfect square number?
Yeah.
Yes. So in this case, we have a perfect square number. Last, you need to ask yourself, do I have perfect square variables? Meaning all my variables have even exponents? Yes, they do. So we can difference of squares this thing. When you do a difference of squares, you're square rooting each term. So that means you square root the 1, the 9, and the x squared. Do each of them individually, and that might help you visualize what you're doing here. So I'm going to have 1 over 3. Square root of 1 is 1. Square root of 3, 9 is 3. X squared is just going to become minus 8. And then it's the exact same thing, but we've done addition. Not so hard, right? It actually makes it look more difficult than it really is. Okay, go ahead, try number 4 on your own. So try difference of squares. I already my answer on 4. All you had to do was square root each individual thing, right? Square root of 9, square root of 49, 4, 25, 81. And all those were perfect square numbers. So it worked out really well for us. Yeah. No, not really. To be frank with you, this is all still math 10. So we haven't hit where we're going yet. Yeah. Like this is still all, everything we're doing today is repeat. Yeah. Okay. Trinomials. The most common situation that we run into in Math 20, and the most common situation you ran into in Math 10 as well, is when you had to factor a 3-term polynomial. And the very first thing you always check for is GCF. Right? So don't forget that step. Even though there's no GCF here, we still had to look, right, and make sure. Sometimes we get so caught up in, oh, I know how to do this, that we forget the easiest thing to do, which is GCF. So, no GCF here. Second thing you do is you look to see that you have a trinomial. And when you have a trinomial, you use something called the diamond method. The diamond method, you draw a beautiful little diamond. I'm going to right here. Yeah, my diamonds are always ugly. The top of the diamond is your A value times your C value. And you'll see they've written that over there on the right. So A times C. Now you need to know what that even means. Your A value is the number in front of the x squared. So your A value is the number right here. In our case, it's a 1. Your B value is the number in front of the x. And your C value is the number that's all by itself. It's not attached to any of the x's. Which is good for anything. You never want to be attached to your x's. Oh, good one. So, I make that joke every time I get the answer. I have a lot of x jokes. Or I have a lot of jokes that are x's. Oh. Savage. Okay, so the top of your diamond is always A times C. So in our case, it's 1 times 15, which is just 15. The bottom of the diamond is the easiest one. It's always just B. Okay? The very bottom is, I literally it's 8. Now the sides of the diamonds. The sides of diamonds are two numbers that would multiply to be 15 and add to be 8. So you need two numbers that would multiply to be 15 and add to be 8. Sometimes it's really hard to figure out what those are. If you're having a hard time, focus on just the multiplication. Because there's an unlimited number of things that add to be 8. For instance, 8 and 0 would add to be 8. 7 and 1 would add to be 8. 6 and 2 would add to be 8. 5 and 3 would add to be 8. And there's an unlimited number of things that add to be 8. So if you're having a hard time finding the sides of the diamond, think about the things that multiply to be 15. It's a much shorter list. 15 and 1, they multiply, but that doesn't add to be 8. 2 doesn't go into 15. 3 and 5 can multiply to be 15, and they add to be 8. Okay? So it's a much shorter list if you just focus on the multiplication side of things. Alright, now that you've built your diamond, that's nice. All you're doing is creating a system that helps you actually answer the question. Like, this diamond is not the answer. Sometimes people literally will just like write out the diamond and like think that they did factoring. This is just how we organize our factoring. Okay? Whenever we factor a trinomial, we leave ourselves with two binomials. So what I like to do is I like to draw in brackets. Because I'm like, I know I'm going to get two binomials. I know when I'm done, I'm getting two binomials. Guarantee it. And my first term in each binomial, because I'm really good at multiplying binomials, I know that's going to create this thing right here. So if I want to create x squared, then I need an x and an x, like that. That's the only way I could get x squared. I know it. So that's why I put x and x as my first term on each thing. My second term in each binomial comes from the sides of the diamonds. Plus 3, plus 5. That is a factored trinomial. This thing right here.
So to get the first thingy for whatever, you
look at your first term in your trinomial. And it's really easy. It's always like a letter squared. Okay, so it's just that letter and that letter. At this point, it's super easy. Yeah.
Is this the same one? Is this the one where you have to, like, if you get a different time, you gotta divide the two sides?
Yeah, we're headed there. We're headed there. All right. We've got two questions here. You're going to try them. Answer them if you want me to do one more. One more? Okay, I'll talk through it. If you want to ignore me, feel free and write it out, but I will talk through the first one. And I want you to try both of these on your own. If you feel like you don't want me to repeat it, then you feel like you're good. So the first thing I'm going to do, I look at this trinomial. I check for GCF. There is no GCF. So the second thing I do is I look and notice it's a trinomial. If it's a trinomial, I use something called the diamond method. The top of the diamond is always A times C. That's the number in front of the x squared times the other number. In our case, 1 times negative 12, so the top of my diamond is negative 12. The bottom of the diamond is always your B value. In this case, the B is negative 1. The sides of the diamond. Two numbers that multiply to be negative 12 and add to be negative 1. This can be a little bit of a harder one. If I'm multiplying to be a negative number, I know that one of my answers should be positive and one of my answers should be negative. That's the only way you can multiply to be a negative number. So what I'm going to do is I'm going to go through the list of things that multiply to be 12. And I'm going to write it out over here real quick. Things that multiply to be 12 are 1 and 12, and 2 and 6, and then 3 and 4. But I want to multiply to be negative 12. So that means it's not 1 and 12, it's negative 1 and 12, or 1 and negative 12, right? A little trick I use is rather than trying to add these together, figure out which one of these would add to be negative 1, I'm going to try to figure out which sets of these numbers are one number apart. Because that would mean if I subtracted them, I would get negative 1. For instance, like 1 and 12, they're 11 apart. 2 and 6 are 4 apart. 3 and 4 are 1 apart. Now I just have to figure out which one of them has to be minus. Easy, right? It's going to be 3 and negative 4. That's the only way I'd add to be negative 1. Perfect. I've set up my diamond. Now I need to turn it into two binomials. So I draw out my fractions or my brackets like that. The first thing in each bracket is whatever would multiply to give me my first term. It's going to be x and x. That's the only way I could create my x squared if I were to multiply these back together. My second term in each binomial is the sides of my diamonds. Plus 3 minus 4. That thing is back. All right, number 3, I want you to try on your own. I'll write up my answer on the board real quick, and then I'll answer some questions on it. So, our problem that we ran into was we didn't GCF it. And then you guys were trying to do that situation where you have to divide something. We're going to do that next. But this is not an example of one of those questions. Okay? This question, you had to do a GCF first and then solve it from there. And that 2 out front from doing our GCF on the very first step is still here. It's the very first thing in my answer as well. That coefficient never goes away.
But later on, you still get numbers.
You'll see. Later on's a whole different situation. And that's like literally right now.
I know. I'm past.
Yeah, well, that's good for you. Because we're not going to go and teach random spots. So, we have questions that are a little bit more difficult. And it becomes a little more difficult when there's a number up front. And that number up front is not a GCF. So your A value is a number that we can't divide out like we did on that last question we just did. So we have to come up with diamond method, but a little bit altered. First thing you check for is a GCF. It's not here. Once you've done that, you create your diamond. So we're going to do our diamond like we always do it. Nothing's changing here. Numbers that multiply to be 6 and add to be negative 7. It's 6 on the top this time because A times C, 2 times 3, is 6. The sides of the diamond, things that multiply to be 6 and add to be negative 7. That one, if you're multiplying to be a positive number, but adding to be a negative number, I must have 2 negative numbers. It's the only situation that would make sense, where you add 2 numbers and get a negative, but if you multiply those same numbers, they become a positive. In our case, things that multiply to be 6 are 1 and 6, or 2 and 3. 2 and 3 definitely wouldn't combine to be 7, but negative 1 and negative 6 would. Now here's how things change a little bit, and it also changes depending on whose class you were in. So, I'm going to show you the way that I do questions like this, and then I'm going to show you the cool ways that Miss Tuck, or Mr. Dunnigan, or Miss Schaub or anyone in the building not named Mr. Kennedy.
Walk around.
Yeah. I basically do my own thing, and they do their own thing. Some people have changed to the way I do it, but I don't remember who's changed. And I think next year we're all going to change, but I'm not upset. No, making waves. So, the way I do it, remember how I said I always want two binomials? Okay, well that doesn't change. I still want two binomials. I know that. That's what every trinomial turns into when I factor it. Remember how I said I always wanted my first term in each to become this thing? Well, how am I going to get x squared? X and x. How am I going to get 2? Well, one of these things has to be 2. That's the only way I'm going to get it to. I don't know which one of these things is going to be 2. So what I do is I make them both 2x, like this. I say, I know I need a 2 out front, and I know I need an x squared out front. I know x and x becomes x squared, but I don't know about this 2. I don't know where it came from, so I put it in both. I'm purposely making a mistake. The sides of my diamond still become my binomials. That's why I like this method, because I still get to just plug these right into my binomials, which is kind of nice and easy. This is not the right answer, because we purposely made a mistake, right? There's no way I can have a 2 first of both these things. So what I need to do is fix my mistake. And I need to check which of these binomials can be divided by 2. Can the first binomial be divided by 2? Can the second one be divided by 2? So that means I should have never had a 2 here. That's the one that didn't need the 2. So I divide that 2 out. I fix my mistake. That 2 doesn't come out front. Right? It's not a GCF. I'm fixing my mistake is all I'm doing. So the final answer is 2x minus 1 and x minus 3. That's how I do it. I'll show you guys how the other teachers do it, because there's a bunch of you who like that method. And so it only makes sense that you see them both, and you can stick with the one you like. I'm never going to dock you marks on something. What you guys do, are you good to erase this? Yeah? Okay. What you guys do instead is you look at your diamond here, and you try to figure out which one of these sides of the diamond can be divided by my A value. Can 1 be divided by 2?
No.
Can negative 6 be divided by 2? It definitely can. So what you guys do is you should write something like that. You write divide by 2 right underneath it, right? Now when you're creating your brackets, the one that didn't get divided by is still 2x. And the one that did get divided by, you also have to divide the front by that. So it just becomes x minus. So your guys' looks a little bit different than mine. The reason I like my way is that I find people who do this way sometimes put this 2 in the wrong spot because they're not sure where that 2 should go. People who do my way, they see the 2 and then they see the 2 get removed, which helps them keep it organized. Yeah, Brett. Yeah, for sure. So, my method. And this is how I'm always going to do it my method. Okay? So my method was, I look at my diamond, and I know I always want to create 2 binomials when I'm done. So I always am looking to create 2 binomials. I know the first term of each binomial has to create this first term of my trinomial. So I know I need to have an x and an x, and I know that one of them has to be 2, but I don't know which one has to be 2. So I just say they're both 2x. And I'm knowingly making a mistake. I don't know which one of these should be 2x, but I know one of them's gotta be. So I just make them both 2x. The sides of the diamond just go back into your binomial. Negative 1, negative 6. Just like they always do. That's not changed. Now I fix my mistake. So I look at my binomials and I kind of ask myself, which one of these can be divided by 2? Which one can I take that 2 back out? Can I divide this first binomial by 2? I can't. Can I divide this second binomial by 2? I can't. So I fix my mistake and I take that 2 out of that binomial. And it becomes 2x minus 1. It becomes x minus 3. So I fix my mistake. The only way people might go wrong on my method, or not the only way, but the most common way, is they think that I've taken a GCF of a 2 out. But I never took a GCF out. I was just fixing my on-purpose mistake. So that's why it can just be divided and it comes out like that. Alright, number 2 we'll do together. So, I look at this thing. I check for a GCF. Please always check for your GCF. In this case, there isn't one. Nothing divides into 15, nothing divides into 17, and 4. Right? No number can go into all 3 of those. So then my next step is that I need to do my diamond method. So I draw a little diamond, which never looks like a diamond. The top number is a times c, so 15 times negative 4. So I need negative 60 up here. The bottom number is always your b value, which is just negative 17. The side values are things that multiply to be 60 and add to be negative 17. If you're not strong at this, make a chart for things that multiply to be negative 20. Sorry, negative 60. Things that multiply to be negative 60 and add to be 17 can be negative 23.
What if you go 20 and negative 3?
20 and negative 3 doesn't add to be negative 17. Right? So you always want to check your signs. And that's pretty common. People would make that mistake. You just always check your signs. Okay, I'm going to do my method. So my method is, I know I want this trinomial to become 2 binomials. So I write out 2 binomials. I write them around the sides. So I write it out. I go 2 binomials. I know that the first term in each binomial has to create my a term here. So I need 15x and 15x. Now it doesn't make sense that they're both 15, but I'm not sure which one really is 15, so I make both 15. The sides of my diamond are the sides. The sides of my diamond go in to become the second term in each binomial. Now I need to fix my mistake, right? Because I knew I didn't need 15 in both of these. So I checked to see which one of these can be divided by 15. Can either of these be divided by 15? No. So this is an even trickier situation. Because this thing can't be divided by 15, and this thing can't be divided by 15. So instead what I do is I divide each binomial by 2 numbers that would multiply to be 15. Because that would be the same effect. Right? So what 2 numbers can multiply to be 15? 3 and 5. Can I divide one of these by 3? This one right here. Can I divide one of these by 5? This one right here. So if you can't take 15 out of just one of them, you break 15 up into 2 pieces and you take 1 out of each. So my final answer here would be 3x minus 4, and then 5x plus 1. If you're not sure, you can always multiply back together, see if you got the original question. Right? Check your answer. That kills.
So your way, you divided 1 by 5 and 1 by 3, those are always back to 15. Why did you do it as
Why did I do 5 and 3?
Yeah.
Like, why did I choose this one to be 5 and this one to be 3?
Yeah.
Because this one couldn't be divided by 3. 20 can't be divided by 3. And this one I divided by 3 because that can't be divided by 5. make sense?
I
Think so? Jared, did you have a question?
I didn't mind it.
Did you get the same answer?
Ish.
Ish. How come, Chad?
What I did was I did 12 and 5. But they, no matter what, they did not equal 8 or 4. But when I did it, actually, I got the same answer.
Oh yeah, I'll come up. Rosie,
Divide
don't pack up. We're not done.
divide the coefficients.
Yeah, you divide everything by 5. Yeah, to get rid of that 15. And everything by 3. Okay, number 3 and 4. I want you guys to do number 3 right now. There's a trick to it, so be careful. But give it a shot. See if you can do it. The trick has to do with that there's an x to the power of 4 and an x squared. That's going to change your binomials a little bit. So give it a shot.